everyone, so this video is an introduction to probability, and we're mostly going to focus on sets, set notation, and Venn diagrams. So let's jump into it. Think about the raffle that we used to do on Fridays. So this is just a quick little intro to probability. Let's say you have like 3 raffle tickets out of maybe 100 that have been given out. Then the probability that your ticket's going to be drawn is 3 chances out of 100 total, which would be 0.03, or as a percentage, if you move the decimal 2 spots, 3%. And the more tickets you have, the higher your percentage is of winning the raffle. That's literally all probability is. Or something like flipping a coin or rolling a die, we can calculate the chance of these different things. First of all, which is more likely? Flipping a coin and getting tails? So the probability of flipping a coin, you've either got heads or tails, so probability of getting tails would be 1 option out of 2, which is 0.5 or 50%. Rolling a die and getting an even number. On a die, you've got the numbers 1, 2, 3, 4, 5, and 6. The even ones are these, which is 3 options out of 6, which is also 0.5 or 50%. So both of those things have the same probability. And that's all probability is. It's just how likely something is to happen. We give it either a decimal number from 0 to 1, or as a percentage, it would be 0% to 100%. So you'll see both, either as a decimal number or as a percentage. If the probability is 0, then it's not going to happen. And if the probability is 1 or 100%, then it is 100% going to happen. Also keep in mind, the sum of all probabilities for a scenario have to add to 100%. Like there's a 50% chance I'll get heads and a 50% chance I'll get tails when I flip a coin, and those have to add up to 100%. Or like rolling a die, you have 1/6 of a chance that you'll get a 1, and then 1/6 of a chance that you'll get a 2, and then 1/6 of a chance you'll get a 3, and so on for 4 and 5 and 6, and all of those have to add up to 1. All right, so real quick, I wanted to mention there is a difference between theoretical probability, which is the probability that you calculate, like in theory, this is what the probability should be, and experimental probability, which is like you do an experiment and this is what you got. For example, we expect for a coin flip, we expect to get tails 50% of the time. That's the theoretical probability. But let's say I actually flip a coin like 10 times. I might not get a perfect 5 out of 10. I would get something close to that, but it might be like 6 out of 10 or 7 out of 10 or 4 out of 10. Also, the more trials you do, the closer the experimental probability gets to the theoretical probability. So like say I did 1,000,000 coin flips, it would be very, very close to 50%, closer than maybe this would be. All right, so these are the kinds of things we're going to be talking about in this unit. We're not going to answer these yet, but I just wanted to give you a preview. So let's say in a bag of 50 Skittles, 10 are green, the other 40 are actual good flavors, because I do not like the green ones. If you pick a Skittle randomly, what's the probability that it's green? Or if you pick 2 Skittles randomly, what's the probability they're both green? Or if you pick 1 Skittle, then put it back, then pick another Skittle, what's the probability that they're green? And these are actually different. So we'll get to those in this unit. Before we do, we need to cover a lot of some notation stuff. So this video is primarily just going to be introducing some new symbols. All right, so in math we have something called a set, and a set is just a collection of literally anything. It could be a collection of shapes, it could be a collection of numbers, it could be a collection of basketball team names, like anything you want is a set, and we usually just write a set in these curly brackets, and we separate each element with commas, and these items in the list are called elements. This is set A, this is set B. If we want to, we could have a subset, which is just like if I take some elements out of here and make a new set, like that's a subset. For example, like let's say we have a set of all the NCAA basketball teams, that could be a set, and a subset would be like just the D1 teams, or just the teams that start with an A, or you know, something like that. Let's see here. Another example of a set could be like all your grades in this class, and then each grade is an element, and then if I wanted to take a subset, I could do just your test grades, or like just the grades where you got an A, or something like that. So those are just a few actual examples. Okay, so let's go with these shape sets here. You may notice that they have a few elements in common, the square and the pentagon. So what I'm going to do is I'm going to make a Venn diagram of these two sets. You may remember doing this back in the day. Whatever they have in common goes in the overlap here, so let's call this set A and this set B. They share the square and the pentagon, so that takes care of these. And then set A also has like a kite and a rectangle, and set B also has a star and a triangle. So this would represent those two sets just in Venn diagram form. And you'll see why this is helpful here in a second, but keep in mind whatever's in A's circle belongs in set A, and whatever's in B's circle belongs in set B. It's just that they have this overlap here, which we can see clearly from this picture. Okay, so now we're going to get into some set notation here. You'll notice that they have some overlap, and so there's a name for this. It's called the intersection. So we say the intersection of two sets, and basically it's just all the elements that they share. So it's just the elements that they have in common. The way we write this is we say A and B. Like the square is in A and B. The pentagon is in A and B. But the rectangle is not an A and B, it's only an A. There's a symbol for this as well. It's an upside down U. It kind of looks like an A for and, if that helps you remember that at all. But these two things mean the intersection of set A and set B. It's where they overlap. All right. So for example, we would say set A and B is equal to the set square and pentagon, because that is where they overlap. Or I could even say the square is in set A and B. There's a symbol for saying that an element is in a set, and it looks kind of like an E. It looks like this. So I know this looks confusing, but what this says is the element square is in the set A and B, because square is in that overlap set. So this right here is like its own set, and the square is in that set. But like the star is not in that set, so we wouldn't say that with the star. Okay. There's another one that we talk about rather than just the intersection, and it is the union. So we've got intersection and we've got union. The union of two sets It's like, you know, like a marriage union, like when you just combine everything. The union means just take all the elements combined. So the union looks like this. It's A or B. The symbol for this is A union with B. Looks basically like a U. And what this means is it's all the elements combined again. It's all the elements combined. So for example, A combined with B. So like take all these elements and all these elements, and you don't have to write the square and the pentagon twice. You just write all the elements that are in either A or they're in B. So A union B would be this set. And it doesn't matter what order you put them in, but we've got diamond and rectangle and square and pentagon and star and triangle. This is the union of set A and B. It's all the elements that are either in A or they're in B. As long as you're in one or the other, you belong in this set. So let's say, is star in A or B? The answer is yes. Is square in A or B? Yes. Is this in A or B? Yes. So all those elements go in this set A or B. So you're going to see both of these formats. You're going to see the words and or, and you're also going to see this symbol and this symbol, and you need to know what those mean. The and, or this A looking thing, means the intersection where they overlap, or this U shape means the union, or basically just all the elements combined. Let's do one more example of this. This time let's do a set of numbers. We've got set X, which is these numbers, and set Y, which is these numbers. If I want to do X and Y, remember this means X and Y, either way, that equals wherever they overlap. So 3 is shared by both sets, but none of these other numbers are the same. So literally 3 is the only time they overlap. And so that is my intersection. The union, X or Y, you could say it with the little u, or you could say it with the word or, is all the elements combined. So, and again, it doesn't matter what order you put them in, but we've got 3, 12, 5, 13, as long as they're in there, 14, 15, 6, and I already had 3, so I don't need to put that one again. It is in there. So this is the union, this is the intersection. Okay, this can get a little crazy. So here's an example of 3 sets, and I want to find the intersection of S and the set, which is the union of P and Q. So maybe pause the video and try this one, and then you can watch me go over it. Keep in mind, order of operations applies. So I'm going to do parentheses first and then combine it with S. So let's start here. Let's do P union with Q. P union with Q is all those elements combined. It's the union of those 2 sets. So I want both of these. I want 6, oops, let's do some brackets, 6, 7, 11, 12, 15, and then also 4, 7, oh, I already had 7, 12 I already have, 15 I already have, and then I need a 20. So this is P or Q right here. Now what I want to do is basically take this and see where it overlaps with S, because now I want to do S and this thing, so I got to see where their intersection is. So basically, what overlaps between these 2? There isn't a 3, there is a 4, 11 is here, 12 is here, and there is no 16. So that's the intersection, and that's my answer for 11 and 12. Oh shoot, did I miss one? Sorry, I think my answer choice is wrong there. I got excited about the 16. But you get the idea. Okay. All right, here's a new symbol for you. I know there's a lot of symbols here. It's a little forward slash. Do you want to take a guess what you think that means? You may have guessed that a little forward slash like this means remove. So basically you have set X and then you remove everything in set Y from set X. It's basically like taking set X minus set Y. It's kind of like that. So for example, if I take set X and remove elements 5 and 3 from it. So here's set X, remove 5 and 3 from that set, and you're left with just 12 and 13. That's it. All right, let's get a little weird now. What if I took set X and removed all the elements in set X? That would leave me with nothing. It wouldn't leave me with 0. 0 is a number, and I don't want to have 0 in my set. I want to literally have an empty set. And so we sometimes write this with just empty brackets. This is called the empty set because it's a set just with nothing in it. Sometimes it's called the null set. And sometimes we write it with this little symbol. It's like a 0 with a slash through it, which means the empty set. So any of these things just mean an empty set. Okay, let's go through an example here. Let's imagine we are rolling 2 dice, and whatever we get, like the sum of what we get, is going to be the outcomes. So there are a lot of outcomes I could get here, and all the possible outcomes make up what we call the universal set. The universal set, again, literally just means all the possible outcomes. Sometimes this is called the sample space. It's the space of all the samples you could get. So for example, when I roll a die, the smallest number I could get would be a 1 and a 1, so 2. I could also get a 3, a 4, a 5, a 6, 7, 8, 9, 10, 11, and I could get 6 and 6, 12. That's the highest I could possibly get. So this right here is the universal set. It's all the possible outcomes of rolling 2 dice, or we might call it the sample space. Sometimes we call this U for the universal set. I realize that's confusing because we already have a U that means the union of 2 sets, so don't let that confuse you. Sometimes it's written as a U with like a fancy looking U. Sometimes it's written as an omega symbol instead. But just be careful. Sometimes it's drawn as a U with a line through it like the real numbers. So that just means the universal set. There's a lot of symbols here, I know. So when you draw a Venn diagram for a scenario, you should include the universe, like all the possible outcomes should be included somewhere. If they don't go in one of the circles, we just put it in a box around the 2 circles. So for example, let's say we're gonna roll 2 dice, and I'm gonna have 3 people do it. We're not gonna actually do this right now, but imagine person A rolls a die and he gets a 2, a 3, and a 5. Let's imagine person B rolls a die and she gets a 5, an 8, and 12. And then let's imagine person C rolls a die and they get, well, let's give them a few more. well, that's okay. They get an 8, 10, and a 7. Okay, so there was no overlap between all 3 of them, but A and B had a 5 that overlapped, so we'll put that here between A and B. And then A also had 2 and 3 that nobody else shared, so we'll put 2 and 3 in A's circle alone. B had an 8 that was shared with C, so we'll put 8 right here. And then also had a 12, so now I have all of B's, 5, 8, 12, 5, 8, 12. And C, we've already got the 8 taken care of, but they also had a 7 and a 10. So it's okay that we didn't have some overlap in a couple places, that's fine. But what I do need to take care of is I haven't hit all the possible outcomes. We've got 2, 3, but nobody rolled a 4. So where do I put the 4? The answer for that is we just draw a big box around the Venn diagrams to represent the universal space. And if nothing, like if I didn't roll one of those options, I'm gonna put it in the universe, but not in one of the circles. So like, since 4 wasn't rolled, we're gonna put a 4 out here. 5 was rolled, 6 was not rolled, so I'll put it somewhere out here in the box. 7, 8, 9 was not rolled, so we'll put it out here. 10, 11 was not rolled, so we'll put an 11 out here. So it doesn't matter where they go, but they're in the universe, but they weren't actually rolled, so we'll just put them outside in the box here. All right. Keep in mind, the sum of all probabilities in a sample space must be exactly 1. So let's go back to that Skittles problem real quick. In a bag of 50 Skittles, 10 are green. So let's go ahead and answer the first question I asked you earlier. If you pick a Skittle randomly, what's the probability that it's green? Well, you have 10 options out of 50 total Skittles, so it's just 10 out of 50, which would be 1/5, or you could say 0.2 or 20%, any of those are fine. Next, I want to know, what is the probability that it's not green? So just use your common sense here. There's a 20% chance that it's green, then there's an 80% chance that it's not green. Or if you want to say if there's a 0.2 chance that it's green, then there's a 0.8 chance that it's not green. What you've just described here is called the complement. The complement is basically everything that's not in a certain set. So this is kind of the definition here. The complement of a set A would be the set of all elements in the universe that are not in A. So for example, let's say my universal set is 1, 2, 3, 4, and 5. Those are the only options I could possibly get. And my outcomes were 2 and 4. So the complement, or like what the stuff that wasn't picked, would be 1, 3, and 5. We denote this with a couple different symbols. Sometimes we use a little apostrophe. Sometimes we write a little C for complement. And sometimes we even do a bar. All 3 of these symbols mean the same thing, unfortunately. They all mean the complement of set A. Basically, what is not A? What's not in A? What's not in A? So in this case, that would be 1, 3, and 5, and all of those things mean the same thing. Or, and this is kind of a weird scenario, let's say the universe is just the colors red, blue, and green. And then my set A is the colors red, blue, and green. What would be the complement of A? In this case, there are no elements in the universe that aren't in A. So the complement of A would once again be the empty set, which we can write either of these ways. All right, let's go through an example here. Let's imagine we actually surveyed the class and I asked people who likes Chick-fil-A, who likes Zaxby's, who likes both, and who likes neither. So imagine 4 people like Chick-fil-A, and 16 like just Zaxby's, and 12 like both, and 18 people like neither. That doesn't feel very accurate, but that's the numbers I have written down, so we're gonna go with that. Okay. So in this only Chick-fil-A bubble, there were 4 people. There were 16 that were just Zaxby's. There were 12 that liked both, so that's the intersection here. And 18 liked neither, so we'll put the 18 out in the universe in neither the Chick-fil-A or the Zaxby's bubble. All right, we're gonna do a few problems here. If we put a P in front of a set, what that means is, what is the probability of that thing happening? What's the probability of like picking an element in that set? So the probability of picking somebody at random from this class, and they like Chick-fil-A. First of all, we need the total for the whole class. This is 30 plus 20, so 50 total people. Okay, so we want to know the probability that somebody likes Chick-fil-A. So that's these 4 people, but it's also these 12 people because they're in the Chick-fil-A circle. They said they liked Chick-fil-A too. So the probability someone likes Chick-fil-A is this 4 plus those 12, so 16, out of the total 50. If you want, you can make that a decimal, but I'm just gonna leave it as it is. Next, the probability that someone likes Zaxby's would be these 16 plus these 12, because they also are in the Zaxby's circle, and that is 28 out of 50. Next, the probability that someone likes Chick-fil-A and Zaxby's. Remember, this symbol right here means the intersection. So where do Chick-fil-A and Zaxby's intersect? And that is just this right here, their intersection. So it's just those 12 people. Next, what's the probability they like Chick-fil-A or Zaxby's? Remember, this is the union of those 2 sets. They might like Chick-fil-A or they might like Zaxby's, just any of those people. Basically, it's all of these circles here, just not the 18 who didn't like anything. So it's the 4 and the 12 and the 16, which is going to be 16 plus 16, so 32 out of 50. All right, next up, I want to know the probability that somebody does not like Chick-fil-A. Remember, that little apostrophe means the complement of. It's everybody outside of the Chick-fil-A circle. It's everybody that does not like Chick-fil-A. So, here's the Chick-fil-A circle. The only people that are outside of it are these 18 plus the 16 who just like Zaxby's. Neither of these liked Chick-fil-A at all. So, 18 plus 16 would be 34 out of 50. Another way of doing that would be, we knew that 16 people liked Chick-fil-A, so basically just do 50 minus 16 and you'd get 34. Or you could have just done 1 minus this. We could do the same thing here. Remember, the little c means the same thing as this. It's the complement of z. It's the people who aren't in z, the people not in z. So if z was 28 out of 50, then we've got 22 left out of 50 who are not in z. And we can see that here, whoops, we can see that here, this is the z circle, and these 22 people, this and this, did not like Zaxby's. All right, let's get a little more complicated here. This is
just a reminder that there's a wedding shower for Chris Gehard at the end of the 200 hall. Thank you.
So this is the intersection of the people who don't like Chick-fil-A and they like Zaxby's. So let's just take this one step at a time. First of all, let's find the people who don't like Chick-fil-A, who are not in the Chick-fil-A circle. So the people not in the Chick-fil-A circle are these 18 and these 16. However, they also have to be in Z. So they don't like Chick-fil-A and they do like Zaxby's. That would be this right here. They're not in the Chick-fil-A circle and they are in the Zaxby's circle. So it's this 16 out of 50. All right, and last one, the probability that they're not in the Chick-fil-A circle and they're not in the Zaxby's circle. So it's the intersection of the not Chick-fil-A and the not Zaxby's people. So the not Chick-fil-A circle would be these two we've already established. The not Zaxby's would be this and this. And the intersection of those is this 18. These people are not in the Chick-fil-A circle and they're not in the Zaxby's circle. So it's just those 18 people. All right. One final bit of vocabulary to go over. Let's imagine we want to make a Venn diagram of set A is all the even numbers and set B is all the odd numbers from 1 to 10. So the even would be 2, 4, 6, 8, 10. The odds would be 1, 3, 5, 7, 9. Notice there is no overlap. So technically, when I drew this Venn diagram, since there's no overlap, I should technically draw them as separate circles. They don't overlap at all. There is no intersection. Like the set A and B, their intersection is the empty set. There's a term for this, and it's called mutually exclusive, also sometimes called disjoint. It means that there is no intersection. The two events literally cannot happen at the same time. For example, you can't be both an odd number and an even number. Those two things are mutually exclusive. And again, if A and B are mutually exclusive, then their intersection is the empty sets, and the probability of that happening is 0. It can't happen. Let's go through a couple examples real quick. Let's imagine we're going to select a person at random from our school. Are these two events mutually exclusive? That they have ridden a roller coaster and that they have ridden a Ferris wheel? Like, could both of those things be true at the same time? Yeah, these could both be true at the same time. So these are not mutually exclusive. That a person listens to Ariana Grande and listens to Anderson .Paak, those are not mutually exclusive either. Those could happen at the same time. That the person is a senior and also is a junior. Those cannot both be true. So this one is mutually exclusive. You can't have these two things happen at the same time. But they have brown hair and brown eyes. Those can both happen at the same time. Those are not mutually exclusive. Drawing a 2 out of a deck of cards and drawing a queen out of a deck of cards. You can't draw both a 2 and a queen at the same time. So these are also mutually exclusive. That you draw a heart out of a deck of cards and draw a queen. You could have a queen of hearts, and so these could happen at the same time, so they're not mutually exclusive. All right. Just want to show you one final example here of combining 3 sets. So this right here says the union of A union with B union with C, which would mean literally all of A, B, and C combined. Is it an A or B or C? Then yes, it's in that set. And I think that's all the things. If I wanted to know like A and B and C, this would be the intersection of A and B and C, which would actually just be this center part right here. So there are ways to combine sets in kind of complicated ways. All right.